G'day, welcome back to Anti-Differentiation with Mr. Hanna. Alright, today we're looking at integration in particular, or more formally we call it the definite integral. And later on I'll mention exactly why integration is slightly different from anti-differentiation, even though at the start it's going to look very, very similar. Okay, so before we start, let me just say a few things. Let's suppose we start with this function over here, and you can see that it is it's a parabola, quadratic equation going on over here. So if we start with that, just a function, let's call it function, and if the function symbol f of x, and here that is looking a lot like a a quadratic function. Now, if we were to do the derivative, its symbol f dash of x, you know that it would form some sort of straight line situation because the order would decrease. So here this is obviously an x squared sort of thing, this would be an x sort of thing. Now, if we were to integrate or anti-differentiate, let me just write integrate for now. Integrate. So let's use the symbol of capital F for the integrand. This would go into a cubic. So it would go the other way, like an x power 3 sort of thing. So obviously going this way, differentiating, and this way anti-differentiating, and obviously those are the opposite things to each other, either going one way or going the other. So anti-differentiating is the opposite thing to differentiating, which you already know. But let's think about more physically in terms of this actual graph, what it actually means to anti-differentiate. So the derivative function is, of course, the gradient. The gradient function is the derivative, and you can see that on the graph because the gradient function is, of course, just the slope function. So like here it's steep and negative, and here it's a little bit less steep but it's still negative, and up here it's really steep and positive, and so on and so forth. It's the gradient function. Now the integral is which is found using anti-differentiation. It's the other very useful thing about graphs. In particular, it is the area of a graph. The area between the x-axis and that curve is what the integral is. So I'm just going to have to show you that, I think, with a few examples. So for this graph that we have over here, this is the graph of f of x is equal to x squared plus 2x. And you can see that's true because it cuts through at -2 and 0. So if we were to factorize, it would be x and x plus 2. So it cuts through at 0 and x is minus 2 for that one there. Okay, so that's the original function. So let's say that I want to find the area of this curve, this bit of area here, this whole bit in here between when x is 0 and when x is 2. That's the bit of area that I want to find. So let's write this down. So we're doing a thing called a definite integral. So it's the antiderivative of our function x squared plus 2x dx, but I'm only finding the area between 0 and 2. So my lower bound is 0 and my upper bound is 2. So we write them there as part of this anti-differentiation symbol. So we can call these either the lower bound and the upper bound, or sometimes they're referred to as terminals. Okay, so now what this is equal to, let's first do the anti-differentiation. So that is going to be a 3 there, and x cubed, Now we need a 1 there, so what we need to times 3 by something to get 1. Obviously it must be a third, because a third times 3 gives 1. Plus, now this is a 1, so that'll have to become a 2. 2 times something gives 2, which it must be a 1 there. Okay, now these terminals, these bounds, we must write those in. So we do that by doing some square brackets and then writing them in here. Lower bound, upper bound. So this is saying we're not finished because we haven't dealt with these bounds yet. Now the way to do this is to figure out this function with 2 and then subtract it using this function when x is 0. So let me show you what I mean. So let's do this whole thing when x is 2. Becomes a third, so a third, 2 cubed plus 2 squared, and then subtract it when 0 is for x. So a third 0 cubed plus 0 squared. Okay, so now we'll neaten everything up. 2 cubed is 8, so that's an 8 on 3. 2 squared is 4. Subtract. Now we've got a third of 0, that's 0. And then 0 squared is another 0. So this whole thing here is 0, and forget about it. So we've got 8 on 3 plus 4. Well, 4 is 12 on 3, so that gives 12 plus 8, 20 on 3. There we go, 20 on 3. That is, so 20 on 3 square units is the amount of area in here, which is roughly 6, a bit over 6. So there you go, there are about 6 square units in here. Now let's try another one, but this time, instead of finding the area between 0 and 2, I want to find the area in this bit here, when x is between -2 and 0. So let me set this up again. Between -2 for my lower bound and 0 for my upper bound. So same function, x squared plus 2x dx. Now I've already done the hard work over here earlier of finding that antiderivative, which is a third x cubed plus x squared. So I've got -2 and 0. So now let me solve this. So first with 0 in for x gives me a third 0 cubed plus 0 squared. Now subtract this with -2 being x. A third -2 cubed plus -2 squared. Okay, so that's 0, so that goes, that's 0, that goes. Now I've got a minus, which is applied to everything in the bracket, so it's going to be minus a third of -2 cubed is times -8. Then remember this minus applies to this as well, so that's a minus. -2 squared is +4. There we go. Minus times a minus is a positive, so that's positive 8 on 3. Take away 4. But we know that, so it's 8 on 3. 4 is a 12 on 3. So our final answer is 8 take away 12 gives -4 on 3. So you go, the area in here is -4 on 3. So you can see that this result is in fact negative. And that's because it's below the x-axis. So whenever it's below the x-axis, you're going to get a negative result for the area. So if we had have done the integral from the area all the way from -2 to 2, so if we had have done this from -2 to 2 of x squared plus 2x dx, our answer would be this big area take away this little area. So it wouldn't have been correct. We would have needed to put it into 2 parts if we wanted to find the total area, because we would have had to make this negative bit a positive bit. So if we had wanted to find the area, the total area, positively, we'd have to have done the positive bit between 0 and 2 of x squared plus 2x dx. And then we would have had to get rid of the negative, To get rid of this negative, we would have needed to do another negative. So we would have needed to do a negative between negative 2 and 0. X squared plus 2x dx. And that would have found us a positive result for the total area. Now, lastly, one nifty little trick when dealing with something like this half of it here. To do with a negative integral, you can just swap the terminals around. So in other words, let me just write it out nice and big. Negative 2, 0, x squared plus 2x dx is the same thing as, instead of having a negative, it's positive now, and the terminals are swapped around. So 0 minus 2, x squared plus 2x dx. So that's a useful trick, being able to swap the negative for a terminal swap. Okay, let's now do a couple of extra examples to get your heads around this fully. So, example 2. Alright, so this time I'm just going to tell you what we're trying to do is find the integral between 1 and 3 of 6x squared minus 4x plus 1 dx. Okay, so we follow our procedure. We're going to be first anti-differentiating. So this is going to be it's x squared, so it's going to be x cubed. And we've got to figure out what the coefficient of that is. So it needs to be something that will get a 6 there. It's going to have to be a 2, because 6 divided by 3 gives 2. Now we've got a minus, so it's going to be a minus, x to the power 1, so that's going to be an x to the power 2 now. And to get the 4, it must have been a 2 there. And here it's just a plus 1, so that must be a plus 1x. And the terminals 1 and 3. Okay, so now first we evaluate this whole thing when x is 3, and subtract the whole thing when x is 1. So here we go. 2, 3 cubed minus 2, 3 squared plus 3. Now subtract it when x is 1, so that's 2, 1 cubed minus 2, 1 squared plus 1. Okay, so now what I'm going to do first is get rid of these big brackets so that I never stuff up my negative thing. I'm going to keep everything else the same. Cubed minus 2, 3 squared plus 3. Now this negative sign applies to everything, all of the terms in there. So it's minus 2 to the 1 cubed. Now a minus and a minus gives a plus 2 to the 1 squared, and a minus and plus gives a minus 1. Okay, now I'm going to evaluate everything. So I've got 2 times 3 cubed is 27, minus 2 times 3 squared is 9, plus 3, minus 2 times 1 cubed is 1, so that's minus 2. 1 squared is 1, so that's plus 2, minus 1. 2 27s is 54, minus 18, plus 3, minus 2, plus 2, minus 1. Now obviously this minus 2 plus 2 are going to cancel with each other. The plus 3 and the minus 1 is going to be a plus 2. 54 take away 18 is 36. 36 plus 2, 48. Oh, whoops. How very stupid of me. 38. There we go. So there's our final answer. 38 is our final answer to our original problem. Okay, I think we're nearly there. Let's do one more, and let's make this one... Actually, I'm going to do 2 more. Alright, so firstly... Okay, this is going to be a graphical one. Let's see. It can be a This can be half. This can be 1. 1. I'm going to make this line the line of y equals 2x minus 1, which means that point there is a 1, 1. This point here, minus 1, will give me minus 2, minus 1. It's not drawn to scale, obviously, because that's a minus 3 there. Okay, and let's put in some shady bits. Okay, and let's say that this question is finding the total area shaded. Okay, find the total shaded area. Whoa, whoops, that means shaded. Don't know what happened there. Find the total shaded area. Now, the first thing I notice is that this bit here is underneath the line, so it's going to be negative, whereas this bit here is going to be positive. So let me write out my full question, and I'll do it right to left. So first, this negative bit, this first negative area, whoops, where am I? Over here, I need to put in a negative sign so that I get back a positive area. So it's between minus 1 and it goes up until, up until here, which is a half. So it goes from minus 1 to positive a half of 2x minus 1 dx. Now we add on our positive area, which goes from a half to 1 of 2x minus 1 dx. Now I'm going to do the trick where instead of having a negative out the front, I can swap the terminals. So it's going to be a from a half to minus 1, 2x minus 1 dx, plus from a half to 1 of 2x minus 1 dx. Okay, there we go. Now let me solve this. So to anti-differentiate 2x is going to be x squared, and minus 1 is going to be a minus x, between a half and minus 1, plus, obviously this is going to be the same thing, an x squared minus x, this time between a half and positive 1. Okay, so let's have a go through of this. So we've got, with minus 1 in there, we have a minus 1 squared minus minus 1. Take away, now with a half, we've got a half squared, take away a half. Now, this second bit, we've got, with x being 1 first off, so that's going to be a plus a 1 squared minus 1. Take away, with a half now, half squared minus a half. Okay, so like before, I'm going to get rid of all my brackets as I go through. So minus 1 squared becomes 1, minus a negative 1 becomes a plus 1. Now here I've got minus to everything in here, so it's a minus half squared. Minus and a minus is a plus a half. Now plus 1 minus 1 minus a half squared. And minus and a minus is a plus, plus a half. Okay, getting there. 1 plus 1, that's a 2. Minus half squared, so that's minus a quarter. Plus a half. Minus 1 and a plus 1, cancel out. Minus half squared, so that's minus a quarter. And plus a half. So we've got, looking at the whole numbers, we've just got a 2. Looking at all the quarters, we've got minus a half, minus another half. So, sorry, minus a quarter and minus another quarter. So that's minus 2 quarters. And we've got plus a half and plus another half. So that's going to be a plus 1, if you like. So simplifying this down, we have 2 and 1 is 3 minus a half, because 2 quarters is a half. So it's going to be 2.5, or fractions are way better. So it's going to be 3 as a fraction is 6 halves, minus 1 of those halves gives us 5 on 2 as our final result. is 5 on 2. So there we go, lots of work to get there, but we got there in the end, finding the integral and finding the area under that curve. Okay, I might do one last example, this one using some unfamiliar numbers. So let's see. Okay, so let's have it as the integral between, say, 1 and... Oh, let's make it easy. Oh no, 1 and 2 of, say, 2x to the power minus 2 plus 3x to the power 1 half, or, yeah, 1 half dx. Okay, this is weird. Okay, we've got a negative and we've got a half here, but we're going to follow the exact same procedure. So, minus 2. Now, we always have to add 1. So, adding 1 to minus 2 gives minus 1. Now, what do we have to multiply minus 1 to get a 2? We have to multiply it by minus 2. Minus 2 times minus 1 gives plus 2. So that's that first bit done. Now the second bit. Here we've got an x to the half, so we need to add 1 to a half. Adding 1 to a half gives 3 on 2. Now what do we need to multiply by 3 on 2 to get 3? And the answer will be 2, because then the 2's will cancel, leaving just the 3. So 3 on 2 times 2 gives us positive 3. There we go. Now we put in our terminals 1 and 2, and we can complete solving this. We have minus 2, and x to the minus 1 is just something divided by x, so minus 2 over 2 plus 2, and then 2 to the power 3 on 2. Now take away everything with a 1, so 2 minus 2 over 1, and then plus 2, 1, so 3 on 2. So minus 2 on 2 gives minus 1, plus 2 times, 2 to the power 3 is 8, but then that will be a square root of 8. So 2 root 8 goes there. Now let's deal with this minus first. So we've got minus and minus is plus. 2 and 1 is just 2. Now minus and a positive is minus. 2 and 1 to the power 3 on 2. 1 to the power anything is just 1. So that's done. And notice that the 2 plus 2 minus 2 cancel out, leaving us with minus 1 plus 2. Now root 8 is really root 4 times 2, and the square root of 4 is 2, so that becomes minus 1 plus, now this bit here becomes a 2 because the square root of 4 is 2, and 2 times 2 is 4, and we've still got this square root of 2 bit here. So there we go, we've got minus 1 plus 4 root 2. And we can also do this exact question using the CAS calculator. So let me just do that for you now. Alright, so grab up our CAS calculator, going into menu, we're doing calculus here, doing the integral. We did it from lower bound of 1, upper bound of 2, and we did 2 times x to the power of minus 2 plus 3x to the power of a half and in terms of x. And there we go. We have our minus 1 plus 4 root 2. So we had the correct answer, which is excellent. Okay, last but not least, I know that there's probably people that have a few questions about this, and I'm going to quickly answer 2 questions that I think some of you may have. So, question 1 that I imagine some people have is, why don't we need to worry about the constant like we did for anti-differentiating? So, why don't we need the constant c? Why don't we need that constant c? Why the heck not? And let me answer that question by doing an example that shows you. So imagine we wanted to do the integral between 1 and 2 of 3x squared dx. Okay, so let's have a look, and this time I'll use the constant c. So this would be, obviously this is going to be an x cubed here. What do we need to get a 3? Just a 1, so we'll leave it. Oh, hang on. Now I'll do a plus c, plus our constant. So suddenly I'll remember to do the plus c between 1 and 2. Now let's see what happens. When we put 2 in for x, we get 2 cubed plus c. Take away 1 in for x, 1 cubed plus c. Now get rid of this, put this negative sign through everything. 2 cubed plus c. Take away 1 cubed. Now minus a plus is minus c. At this point you'll see that we've got a plus c and a minus c. So those constants, no matter what they are, will always cancel out. So in this example we have here an 8 minus 1, 7. So we get an answer even though we don't know what our constant is. So the key message is the constants cancel out every time. Okay, and this is actually the big difference between integration and anti-differentiation. Is anti-differentiation, you need the constant. Integration, you don't need the constant. And that's the big difference. Okay, very, very last thing. Another question that many of you may have. Question 2 is, why does the integral give you the area? Oops, give you the area. Why? Why, oh why is that the case? Which I haven't explained. I just told you it is the area, so deal with it. But you may be wondering why. And essentially the answer is that the fundamental theorem of calculus tells you that it is. That's one of the answers. So it's all about the fundamental theorem of calculus. And it basically says that if big F of x is any antiderivative of some function of f of x, so f of x must be, so any antiderivative of f of x which is continuous over the domain A to B, including A and B, then, okay, this is the main part coming up. Oops, this should be a then. Okay, so if we've got some antiderivative f of x, it's the antiderivative of a function f of x, and that function's continuous over some domain. So in other words, we might have, who knows, some wiggly function, and here is A and here's B, and it exists, and it's nice and smooth and continuous. Then, then the fundamental theorem of calculus says that for basically exactly what we've been doing. So between the terminals of a and b, our original function, when it's integrated, gives you that antiderivative function from terminal b, take away the antiderivative from terminal a, and that's all there is to it. And so it means, and this thing saying any antiderivative means that there's no constant. So this thing here is the fundamental theorem of calculus. It basically is just what we've been doing in this whole video. Now, many of you will probably see I haven't actually answered the question of why does the integral give you the area? Why is that? In order to answer that, I need to be able to prove the fundamental theorem of calculus. I need to prove that thing to you. I need to show you that it's correct, and I will do so, but this video is super long already, so I'll do that in the next video. And the next video is going to be me showing you why the fundamental theorem of calculus is true, how it came about. And it's going to be a video that you only need to watch. You don't actually need to do any calculations of your own for that one. So there we go. Well done for getting through this entire video. And I shall see you next time. Goodbye.